Today, you'll be hearing from Upstream Tech co-founder and CTO Alden Keefe Sampson about lessons from 6 years of AI hydrology in practice. Alden is going to walk us through the ways that HydroForecast uniquely translates hydrologic science in the context of deep learning and a bunch of lessons that our team has learned along the way. If you have any questions as we go along, please use the Q&A box at the bottom of your Zoom screen, and we'll cover as many as possible at the end of the presentation. Alden, I'll hand it off to you.
Thanks, Abby, and thanks everyone for joining us today. All right, I'm going to dive right in. Like Abby said, I'm going to talk about AI hydrology in practice, what we have learned while using these types of models to make operational streamflow forecasts. First, a little bit about ourselves. We are Upstream Tech, a team of 35 people with backgrounds from software engineering and machine learning, all the way to water resource management and earth sciences and environmental management. We make HydroForecast, which is a streamflow forecasting service. And that's what I'm going to be talking about today. We've been doing this now for about 6 years coming up on 7 years, actually, of operationally forecasting using AI, which 6-7 years is not a very long time in the history of many things, but for using AI in practice to inform operational decision making, it's actually a relatively long time if you think about how long AI has really been at the forefront of many people's minds in terms of a new technology to use. So before we dive in, I wanted to get all on the same page about what I mean when I say stream flow forecasting. This is how much water will flow down a river or into a reservoir over the next few hours, over the next few days, or over the next few months. It's really asking that question. And the answer to that question is a combination of what's going on in the weather, in the atmosphere, and what's going on in the land, on the surface of the land and below it. And those two factors combine together to ultimately produce runoff, which comes from the land into the river, and stream flow that goes into our reservoirs or through our stream gauges and the water that we use every day. So today, I'm going to talk about our streamflow modeling approach at a high level, how we think about how to model streamflow with AI. Then I'm going to get into some of the techniques that we found most effective as we've been building and iterating on our processes over time. And then finally, I'm going to step back and ask what lessons from these effective techniques that we have found we can draw about using AI to model the Earth and other Earth systems more generally, because there's a big explosion in that type of modeling, and I think it's really exciting. So let's dive right in. First, I'm going to tell you a story. So back this was fall of 2019, we were a young startup company. We had been going around to conferences talking about how we were making streamflow forecasts using this new technique called machine learning. That at the time, it wasn't AI. And people were interested, but also very skeptical. Many of the users make really important decisions with water forecasts, and they're not about to, make multi-million-dollar or very high-stakes safety decisions just using some new thing they picked up from some person who approached them. So they were curious, intrigued, but wanted to make sure that there was something there. And so they had been talking about it amongst themselves within this industry group and decided they wanted to run a competition. And so we got the call, hey, would you like to be part of a 1-year live forecasting competition? So of course we said yes. This began a rather stressful, high stakes year for us. We went into the fall. There's lots of rainstorms going on then. It wasn't always immediately clear how we were doing compared to other people. We just had to put our best foot forward every day. And then there was a third party, the RTI, the Research Triangle Institute, who'd been contracted to collect all these forecasts from us, from the NOAA river forecast centers that are all around the United States, from some of the best in-house forecasting teams up in Canada and the United States, who operated very large hydropower installations and therefore had teams whose job it was to do this forecasting, as well as just competitors out on the internet and other research labs and other companies. So we were all putting our forecasts in. The year started to come around. We really still didn't have good visibility into how we were doing, but it was very exciting, and we were continually honing our models. But this was really cool for us because this is really the gold standard of a test. There's no way to overfit your model on the future because it's never happened before. And just every day was get your best forecast in by the deadline. So at the end of the day, end of the year, the competition wrapped up and they published the results. And we had won 23 out of 25 possible categories, including every single geographic region in the all-around category. And this was a very exciting result for us, as you can imagine, and definitely caught the attention of a number of the larger water users and water managers in the world who saw that in an operational setting, this type of technology was really able to perform. So fast forward to now, we are forecasting in 14 countries across 5 continents. We work with a lot of hydropower operators, some irrigation, municipal water supply, and environmental groups. We forecast across over 850,000 square kilometers of area of the land, and we inform over 10 gigawatts of hydropower installations. So what were some lessons from that competition? One was that we saw very wide variation in performance among models, which you could broadly group as statistical or machine learning or AI approaches. Some of those approaches were actually the least accurate at some sites and regions. And others were kind of in the middle, and ours were in each region, like I said, was the most accurate. And the main takeaway from this is just using AI or just using machine learning isn't a solution in itself. How you apply these technologies really, really matters. A second was that we got to see how these approaches perform in an extreme year. One common question that comes up when you use machine learning models is, well, these models learn from past data. How do we know how they're going to perform when they see conditions that they've never seen before? And in water forecasting, these are some of the most interesting times for forecasting. When things are just as they are usually, that's not a very interesting time for forecasting. When people really care about how good your forecast is when unprecedented events are happening. So in this case, it wasn't a particularly extremely wet year, but it was a very dry year. In fact, in California, it was the driest year since 1924. And that meant that our model had never seen conditions as dry as it saw during the forecasting competition period, because our 1924 was many years before the start of the data that our model had trained on. This was truly an out of sample extreme event. And in California, the model did exceedingly well. That was one of the locations where we won every single category. So here is one more piece of information that shows that when used properly, these techniques can extrapolate and generalize in ways that are actually stronger than some of the traditional approaches. So what is our approach? Let's get into it. Broadly, we take what we call a theory-guided AI approach to forecasting streamflow. And what I mean by that is really we apply what we know from hydrologic and atmospheric science to each step of the modeling process, and each step of a deep learning modeling process. So this is using neural networks at the core of our model. But we're not just throwing anything at the wall that will stick. We're really being very thoughtful about every step of the process, informing that by what the physical science tells us. So what that looks like in practice, starting at kind of the top of the pipe, the modeling process, in terms of the input data that we use and the outputs that we're asking our model to learn to predict, we choose those and pre-process those data based very specifically on hydrologic theory. So for example, we know that snow information is really important. So we're going to make sure that there's inputs that can tell the model about snow. We know that precipitation is really critical. So we're going to give our model multiple different views on precipitation. And then we also know that there's some inputs that should not be impacting stream flow. Like, for example, the population in some certain region uh, that may impact water withdrawals, but that's not physically impacting the amount of runoff that's coming from the basin. So that shouldn't be a input to a model that's trying to predict natural stream flows. Another one is the day of the year. The day of the year is a great proxy for what stream flows will be, but during climate change, what stream flows will be at different days of the year is going to be changing. And so we don't want our model to learn to just take a shortcut from day of year to stream flow. We really want to give it the inputs that change seasonally along with the day of the year, and learn and have the model learn to translate from those inputs directly the weather conditions to stream flow. So if those conditions start changing and shifting as we expect under climate change, our models will be reacting accordingly. Second, in terms of the model structure, we align how we build these neural networks with how we know water moves physically. So at every single time step, the model is keeping internal states about the hydrologic conditions in the basin, and it's passing those states on to the next time step. It's taking in new information about the conditions at that time step, incorporating those into its states, and then outputting a new stream flow prediction. And then similarly, we actually explicitly represent the river network within the neural network. And I'll go into that a little bit more. In terms of how we train the model, we specifically set up the training process to ask the model to learn relationships that hold true across space and time. So as we change locations, as we change places, and relationships that hold true across space and time, those are effectively, that's how you describe physical laws. So what we're asking our model is to learn physical laws, not time and space specific relationships that are more brittle and won't generalize as well as we get into new conditions. And finally, in terms of evaluation, we do most of the evaluation exactly the same way that you would do a strong classical hydrology model evaluation. We're looking at quantitative metrics, we're looking at qualitative plots, and then we add in one additional piece, which is we can actually look at the learned relationships that the model has learned during its training process. And I'll show you an example of how we do that. So I mentioned just a moment ago about how the neural network structure is actually represents what we know about water. And let me go into this diagram a little bit more about what I mean by that. So first, we divide up our river basin into subbasins that are based on the connections in the river network. So for example, at a confluence between two tributaries, we'll split that into two different subbasins. And then the model sees a value for each of the inputs that's averaged across each of those subbasins. And then it also sees the river network, a graph of how each of those subbasins connects through river reaches to flow water down through the river system. So what's happening at each one of these little subbasins is we use a model, a neural network building block called a LSTM, or long short-term memory. And that takes in, it's a time series sequence model. And at every time step, it takes in new information. It updates some internal states, and then it outputs another value. And in our case, the value is a probability distribution of the model's expected stream flow at that point in time. In this case, actually, it's the runoff from that subbasin. And then those runoffs from each of these subbasins flow into a graph portion of the neural network, which explicitly models the flow as it moves down and takes time to travel through each reach of the river network. It adds up flows when you get to confluences and continues all the way down. So we can make dense stream flow predictions at each outlet of each subbasin. We also add in locations where there's a stream flow gauge, and that allows us to integrate upstream stream flow observations, which is really helpful for short-term forecasting. And this whole entire thing that I just described is trained end to end. And so that means that the river routing component of the model and the subbasin runoff component of the model is all trained to work in harmony together. And it allows us to do some really useful and interesting things in terms of assimilating stream flow gauge observations as well. A really key important part of this process that I was talking about in terms of how we train the model is this two-phase training process that we use. We use large diverse data sets, particularly during this first phase of the model training process, where we're training a base or foundation model. This is where the model is learning the underlying hydrologic relationships that it's going to rely on. We train this model across many, many different locations and many years of time. And this is really when the model learns the most. This is where it learns to model and understand hydrology. And the key here is that we also tell the model how each of the basins, the characteristics of the basins, so how they are similar and different, because the exact 1 inch of rain in one basin is not going to necessarily produce the same stream flow response that you would see in another basin. In order to let the model figure out why, we have to provide additional information like the slope and the elevation and satellite observations about what's going on the land surface, so that the model can learn to bring all that information together and predict the stream flow that's relevant for that particular basin. We have a second optional step that we call tuning. And this is where we take that base model that was created in the first step and do additional training at a specific river basin or a handful of river basins. This is the step where the model's learning particular nuances and details of that specific river basin. And I actually have a note here. Ideally, this step wouldn't exist. If the model had perfect information on everything that was going on in every single river basin, you wouldn't need to have this step. But there are things that we fundamentally do not have observations of that are going on in river basins. And this step in practice turns out to be useful for squeezing out a few more percentage points of accuracy if you have streamflow observations in a particular location. If you don't have streamflow observations, you can just stop at the first step. And that's really still a very strong model for doing ungauged streamflow forecasting. All right, so that's kind of broadly how we go about and think about this process of modeling streamflow. And now I want to get into some particular interesting techniques that we found to be effective. So one is taking advantage of satellite land surface observations. So like I said at the beginning, streamflow is a product of the weather and the land. And many traditional hydrology models really just focus on that weather component and then try to model the land entirely. But with satellites, there is this wide array of direct observations about what's actually going on the land. And the physical science tells us that the snow processes, the amount of vegetation, how those things are changing over time, those we know from science are going to be influencing streamflow. So if we could get observations of them and provide that additional information to the model, it might help the model be more accurate in those types of situations. And what we've found is that's exactly true. So what this plot that you're looking at right here is the model accuracy of a couple different experiments. Each of the colored lines is a different experiment. And what varies between each of those experiments is how much satellite observations were available to the model. And our original model is this orange line here before the experiments, which didn't see any satellite data. And it was performing basically across this curve is how does the performance change across many different sites. And so the sites that are up here in the upper right-hand corner, these sites are already performing very well. The sites down here, these are the sites that are not performing as well. And what we see is when we add in satellite data, it increases the accuracy the most at the sites that are performing the worst, that are the model's having the most trouble with. So what's going on here is that the model had most of the information it needed to make good predictions at these other sites. Down at these sites, the model was missing some pieces of information. And by adding in this satellite data, it was able to gain further information that could then use to improve its streamflow predictions. On the right here is just some examples, some snapshots in time of this is a vegetation index, which is very low when you have snow. So you can see the white here is very low values of it. That's basically a snow on mountains in a valley melting over the course of spring. And so this information is really telling the model, giving it like a live view of exactly how much snow is left in the basin. So a takeaway for this is when you're evaluating a model, look for the conditions that it's performing the worst in and ask what information might this model be missing that would help it perform better in these particular conditions. Another thing that has worked excitingly well is actually, you could think about it as an extension of asking that question, what information is missing? So we began by modeling natural stream flow, but many rivers in the world are very altered by humans. And the piece of information that was missing from our models that model natural stream flow is what are the human alteration impacts in this river basin? So we developed a second model that is able to see many, many more inputs that tell it about the types of human alteration that's going on upstream in the basin. And those models, we can then look at the predictions of them side by side. And what we see here on the top is a model that's designed to predict unimpaired flow. And you can see it following kind of a natural stream flow pattern where there's rises in the spring as the snow melts and the rain comes, and then it drops back down. You have another storm, and then you have a very dry summer period and some more storms in the fall. Then you can see this is the model that was asked to predict what actually happened and given the information about what humans are doing upstream of it. And it's able to say, actually, I see that there's some dams upstream, and I'm going to predict a much more muted, consistent flow value throughout the spring because I know that the way people use dams in these types of conditions is to absorb excess water and then slowly release it later on in the summer. And so it was very exciting for us to see that the models, when given this additional information on this very complex question of how are humans modifying stream flow, was able to tease out how those human impacts would be interacting with the weather and the natural land surface runoff. Now, I should note, this was solely by adding additional inputs. We made no other alterations to the neural network structure. It really was about providing new information to the model. Another core thing that we do is provide multiple weather forecasts to the model in parallel, going into every single prediction. We know that every single weather forecast is wrong in some way. And so the approach we take is give the model multiple of them at once and let it learn to use the mutual information between those forecasts in order to make a better prediction. This helps both improve our mean prediction, but also inform the uncertainty bounds that are predicted by the model. This plot on the right here shows each of the green bars was the distribution of performance when a single weather source was used. When you add two weather sources together, it starts to creep up. And then the best performance is from combining multiple, in this case, 3 weather sources together. In the competition, we used NOAA's GFS forecast and the ECMWF, the European Center's high resolution forecast, and we've added more weather forecasts since then. All right. This one is some of our cutting edge research and development to being resilient to missing inputs. So missing data is a fact of life in real-time forecasting. Weather models have problems being produced. Stream flow gauge data gets interrupted. Satellites run out of funding or have their ground connection broken for some amount of time or drift in their orbit. And it's really valuable to have a model that can automatically handle those missing data and use whatever data that is available to make the best prediction at hand. So we do this by providing both the inputs to the model as well as a parallel set of inputs, which are flags that are a 1 if the value is there and present, and a 0 if the value is not available for that particular input at that particular time step. And by changing the ratios of missing data available in that base model training step, we're able to train the model to learn to adapt to when there is missing data and take advantage of the the data that is available. This also has a really kind of interesting feature that falls out of it, which is you can apply what if scenarios. You can mask out data that you technically have, but for example, you might want to say, what would the forecast be if it only saw the forecast from the weather forecast from the European Center? Oh, well, we can mask out all the other weather forecasts and provide it just that forecast and see what the prediction would be. This is something that was actually been pretty active research and development, and we're now rolling out in our short-term version 3 models we would call ST3. Astute observers here might notice that the blue line here, which uses all the forecast sources, is higher than any of the rest, which is something that you wouldn't necessarily hydrologically expect to happen. And this harkens back to the way we evaluate our models. We make sure we're wearing our physical scientist hat when we're looking at these models, not just looking at raw statistics, but saying, is the behavior of this model make sense? In this case, that does not, and that's something that we've addressed in further R&D. Okay, another thing that has been pretty, it was a really interesting finding for us, was that multitask learning improves the physical fidelity. What I mean by that is asking the model to do multiple things at once to predict multiple related but different inputs can improve the physical realism of both of those predictions. So here's an example from our long-term climate-based modeling. In this particular example, we are working at a river basin that has a glacier in it at the headwaters. And the customer here was really wondering, in the long term, how are my late summer, August and September stream flows that are primarily driven by melting glacier at that time of year, how are those going to change over the next coming decades under multiple climate change scenarios? And what we found is that when we ask the model to predict not just stream flow as its output, but also the snow and ice cover that the satellites have observed at the same time in parallel, we end up getting better predictions for stream flow than we were getting when we just asked it to predict stream flow only on its own. And what's going on there is that asking the model to explicitly output predictions of the glacier is requiring it to maintain better internal fidelity and realism of modeling of what's going on in that glacier. And that improved internal glacier information makes its way into the stream flow prediction as well. And we see relationships that make much more qualitative sense when we evaluate these models. In this case, you can see that this was a very hot climate change scenario. And you can see how that actually causes very slight over the coming decades increases in stream flow at this time of year until it hits a point where the snow is almost entirely gone in the glacier. And then you really start to see in this warmer solid line scenario, the stream flow drop off a cliff at that point. So this is one of these like nonlinear effects that we really hope we're not running into in the future, and why we should really do our best to not become in those climate change scenarios. All right, the last effective technique I want to share with you all is how we look inside the neural networks to see and explore what they have learned. So people often describe neural networks as statistical approaches in general as like a black box, as if you couldn't look inside them and understand what they have done. In fact, there's a number of techniques broadly under the umbrella of explainable AI, which allow you to very specifically ask your model what it's doing and why it's doing what it is doing. And in this case, we use something called integrated gradients that allows us to ask what inputs are influencing the streamflow output to be either higher or lower the most, and at which time steps are those inputs having the influence. In this particular prediction, what we've set it up to ask is, across this whole spring period from April and May, which inputs are causing there to be more runoff stream flow in that time period or less? And what we can see is the model has learned that these pink events, pink peaks right here, this is the precipitation back in the winter when it was cold, accumulating as snow, and it's now driving additional stream flow during the spring as we're melting. Well, what's melting it? We can look forward during this time period and see this brown line here, where that's the solar radiation. So the solar radiation, the model is saying, I'm looking at the solar radiation input over these time steps and that's the one that's driving increased stream flow during this time period of year. Of course, you can see there's many other inputs that are having smaller but reasonable effects as well. And so this is one way that when we have a model that's making predictions that qualitatively and quantitatively look reasonable, we will then put it through this filter of, is the reason that it's making these predictions realistic, and does that jive with our physical understanding of how hydrology works? And if it doesn't, we will reject that model and use a different model, because we want to make sure that in operations, our models are making predictions based off of relationships that really should hold true. Here's just a different view of taking the same approach, but rather than really looking at it over time, this is looking at it over space. So this is over a prediction during October in also a very snow melt driven influenced area. Particularly, there's some glaciers up here in these subbasins up at the headwaters. And what we can see is that the base flow at this time of year, the stream flow that's remaining in October before the rains have picked up again, is really particularly driven by these specific subbasins. And if you go look, these are the subbasins where the glaciers are. So this is what we would want to see. It jives with our physical understanding, but it's really valuable to be able to check that the model has actually learned what we hope it would have learned. All right. So those are some of the kind of particular things that we've found interesting and have worked best for us. But stepping back, what can we take from this experience that might inform how we go look at AI for Earth systems modeling more generally? There's a lot of really exciting work being done in AI numerical weather prediction for the atmosphere. People are making entire Earth system coupled models using AI. Many other parts of groundwater and other systems are being now modeled using AI approaches. So it's a really, really exciting time to be in this field. So if to anybody working on those problems, these are my takeaways for you. The first is, you don't have to play the same game as the traditional model that's been being used for this approach. Another way to say this is, go beyond making an AI emulator for blank. That may be exactly what you need, but it's a chance to take, starting with these new AI models, these are a chance to take a fresh look at what the user needs. There are many characteristics about the outputs of our traditional models that are really byproducts of what was possible or how the model works internally, and particular constraints that may have been present at the time and may still be present, but may not be constraints on your AI model. So this is a moment where you can step back and ask, what does the user really want and need? For example, maybe in terms of an AI weather model, what people really care about is high resolution accuracy right at the surface where 99.9% of us live. And maybe the other layers of the atmosphere, we don't need the same spatial resolution, but what we would really like is just extreme spatial resolution at this surface. So, maybe we can reduce the amount of computing power we're using to model all the way up to the stratosphere and really focus on the surface. Or the time step that your model runs at. Many models are running at a particular time step because that's what the physical equations that we had could let us do. But maybe we want higher time steps, or maybe people really are just wanting to know across the next entire season, can you just tell me a probability distribution about whether we're going to be high or low on some particular quantity that I care about? And that might allow you to make a more accurate prediction of that ultimate quantity that the user really wants. And then take a look at new capabilities. So AI models are able to do things that we couldn't do with traditional physical models. For example, we can directly use all types of many new types of observations that just by providing them as inputs to the model that we didn't previously have methods to assimilate into our models. That's one of the strongest ways to improve your predictions is really include new pieces of information that you weren't able to incorporate before. And if because you're using an AI approach, the AI model is able to figure out how it should incorporate that information rather than you having to spend, maybe an entire PhD trying to figure out how that should happen. Another example that I didn't get into as deeply is uncertainty estimation. There's ways with neural network models and other statistical models to predict the uncertainty of your, as well as the mean prediction right from the start. That can be just built into the model and incorporate many different sources of uncertainty in your modeling. And then finally, in terms of new capabilities, look to the explainability approaches under that explainable AI umbrella. In some ways, these models can be more complex and harder to tease out why they're doing what they're doing. But in others, these explainable AI techniques can actually give us a stronger and more concrete explanation of why the model is making a particular prediction than we could actually really get from our physical models in the past. So that's my pitch to you. If you work in AI Earth systems models, don't just make an emulator, really step back and think about what the users want and what we can do now with these new approaches. Another big lesson is that data and compute almost always in the long run are a better approach than trying to be very clever with our models. This is a reframing of Rich Sutton's bitter lesson, which he said, general methods that leverage compute are ultimately more effective than methods that embed domain knowledge in the model. We thinking we're, smart scientists have tried some things like building in conservation of mass and energy constraints into our neural networks. And because, if we know anything about the world, at least like conservation of mass and energy has to be true, right? Well, ultimately, this actually did not improve streamflow predictions because we don't have complete observations of all the fluxes going in and out of streamflow, out of a river basin. And it's actually valuable to the model to be able to account for that uncertainty that we have and then incomplete total information that we have. Another thing that we tried that didn't work was having the model learn to partition precipitation into rain and snow explicitly. And then maybe that would help the model downstream of the further steps in the model to better model stream flow. And it didn't actually help. The model was able to do it. Model's kind of just like, to personify the model, it was like, yeah, I can jump through that hoop if you need me to, but that's not really how I'm working internally. And you spending time trying to code up this very clever thing inside of the model is taking time away from bringing in better data to the model and leveraging the scale that comes with additional computing. So to draw that out as a graph on the right-hand side here, I would say that streamflow is really kind of just past this inflection point or this crossing point where when you have very small data sizes, embedding your human knowledge in the model is helpful. It'll get you a better model faster when you don't have that much data. But as you start to have larger data sets and access to more compute, and we're getting out to this portion of the graph, you can ultimately, you will go slower by spending a lot of time trying to embed these constraints and are like ideas that feel clever to us in our model. And rather we should be taking the time, because our time really is zero sum, take that time to improve the data that we're bringing into the model and use approaches that can really leverage and scale when you add additional compute to them, like deep learning models. So that whole lesson, though, it's called the bitter lesson because it is a little uncomfortable as a physical scientist. It can leave you wondering, so if my knowledge isn't useful to improve the core of this model, like, what should I be doing? What do I have to offer to this process? And here is my take and what I believe on that in terms of what is the role of scientists when building AI models in this new world. The main and one of the most important roles is posing the problem to the model. This is about, are you asking a clear and answerable question for your model to solve for you? And are you giving it the right data? What data is relevant? What data is not relevant that you should not allow the model to see? And in your data, what structure is there between the data? And are you providing that structure to the model in the way that it can interpret it? For example, sequence relationships and spatial relationships. Is that in the inputs that you are providing to the model? Or is it just seeing a whole big collection of unstructured numbers? This change from spending a lot of time really building the core of the model to helping the model pose the right question to the model is maybe a little analogous to going from being like a research assistant to leading a lab, where you're really helping the people that you work with as a lab leader think about how to approach this problem and you're helping evaluate it and helping them, when it's not performing as well, think about what new approaches to take, how to change how you're viewing the problem, what new information to bring in. That's one way I think about what is our role. Another, an incredibly important role as scientists building AI models is determining and communicating fitness for use. In short, like, when you have a model, can we trust this thing? And what can we trust it for? You are the expert that the rest of the world is looking to ask, can we use what you are providing or what somebody else is building? And how much trust in it should we place, under what conditions, and what things are ready for use and what things still need some work. I find this still really exciting, that how you pose the problem to the model, it doesn't mean you're not building models anymore. It's really kind of a different way of thinking about the model, and you still get to do quite a bit of the types of coding and data science that I find really exciting. So with that, I'll just end with, this is a really exciting time to be building these types of models and doing this type of research in earth sciences. And I hope you all enjoy it as much as we all do. Thank you. I'll now pause for questions and take a sip of water and check out the questions that have been left in the comments.
Yeah, thank you so much for that, Alden. That was packed with insights. We covered a lot. We talked about the modeling process for HydroForecast, effective techniques based on your experiences over the last several years, and then some broader lessons for AI and Earth systems modeling. For anyone who has questions, there's a Q&A box at the bottom you can use. I see we've got one question already about how river routing is implemented in our system. Sina asks, could you please clarify whether river routing is implemented as a differentiable routing layer, such as Muskingum Kunj, or as a graph layer with an adjacency matrix?
Great question. Hi, Sina. So it is implemented as effectively, we are predicting a unit hydrograph at every single reach, river reach or edge in the river graph. So what's going on is we've got our runoff at particular nodes that are coming into the system. And then for each reach, there's a very small little subcomponent of the neural network, which looks at the runoff as well as some characteristics of that particular reach, and the runoff at that particular time step and the characteristics of that particular reach, and it predicts 3 values. The first is the mean travel time delay that expects the water to take as it flows down that reach. So this would be like if you're looking at your unit hydrograph and it's got it's parameterized by some function. We parameterize it by a normal distribution, and so we're predicting the mean of that normal distribution. The second parameter that this little subcomponent predicts is a standard deviation. So of that unit, that normal distribution. So how much the water is going to spread out as it's traveling down that river reach. And then finally, we have a third parameter, which is a volume gain or loss. This is initialized so that there is a conservation of mass. There's no volume gained or lost along particular reaches, but we do allow the model to learn that this reach is a little bit of a losing reach or a little bit of a gaining reach in a way that's not accounted for by just additional runoff that's coming along from the local subbasins along the way. This is regular. That component is regularized to really encourage it to maintain conservation of the mass of the water that's flowing through the system, but we do allow a little bit of wiggle there, which we find helpful. So the short then how this all works is we work down the river network. So starting with the leaf nodes of the graph, so the highest tributary nodes, and work down delaying flows using that unit hydrograph approach at each reach, at each time step, and then adding them up at confluences and repeating that process through all of the reaches down through the river network. Did that answer your question?
We'll give folks just another minute to jump in if there's anything else you would like to hear more about or that was unclear that Alden covered. We're happy to talk more here. All right. Well, if not, really appreciate everyone's time. This webinar was recorded and we'll send this out to anyone who registered. Any closing thoughts from you, Alden?
Oh, thank you all for joining. And if you have further questions, my email's right there, or feel free to email team@HydroForecast as well. Thanks for joining, everyone.
Thank you.